This lesson deals with junction field effect transistor characteristics. You can find these notes in the ECE302 ebook in Chapter 4, starting on page 1. There are two types of junction field effect transistors that we call JFETs. One's called an N channel, the other one's called a P channel. The N channel device has this schematic symbol with an arrow pointing in at this straight line. The N channel JFET has three terminals, a drain, gate, and source, and then voltages and currents associated with those terminals. We'll call this voltage VGS, the gate source voltage, this the drain source voltage, V sub ds, the current coming into the drain, I sub d, the current leaving the source, I sub s, and the current entering the gate, I sub g. If we plot the gate source voltage versus the gate current, we get a diode type characteristic. If you plot the drain source voltage versus the drain current, you get a family of curves. For the gate source voltage of 0, you get a line that looks like this. As that gate source voltage gets a little bit more negative, that curve drops, and then drops some more, and eventually it hits 0 current. And that's the case where the gate source voltage is equal to a thing we're going to call the pinch-off. Now note this is very different than the BJT, where we were varying current in the base. Here we're now varying the gate source voltage. This region here we're going to call the ohmic region because it looks very linear over a larger change of voltages than the BJT. This region over here we're going to call saturation. It's actually the current saturating. In other words, the current's not changing for a change in voltage, but most textbooks just call that saturation. And then the case where there's no current flowing, cutoff. How do we make an N-channel JFET? We take a piece of silicon, it's actually rectangular in shape, and dope part of it N-type, and dope the sides P-type. So we'll attach a terminal here, call that the drain, call this the source, and then for the gate, we're going to connect these two side pieces of P-dope material. The gate is P material, and the source is N material. We have a diode between the gate and the source. So plotting the gate current versus the gate source voltage is not surprising. We see the characteristics of a diode. We're going to operate the gate source voltage to either be 0 or negative, and we do that because the current over here is 0. The voltage is controlling the flow of current, and not a current controlling the flow of current. In a sense, what we're having here is a field effect that's controlling the flow of current. On the circuit symbol, we had an arrowhead going from the gate towards the drain and source, and that's because there's a P-N junction here where we show the tail of the arrow by the P and the head of the arrow by the N. Suppose you apply a voltage between the drain and the source, and between the gate and the source. Let's make the gate source voltage 0, which would mean this is a short circuit. Suppose that we pick the drain source voltage to be in this neighborhood over here. In other words, a pretty small number, maybe 1/10 of a volt. The voltage between the gate and source is 0, and the voltage between the gate and drain would be 0 minus 0.1. This voltage here would be a minus 0.1 volts. Well, the voltage across this P-N junction is negative. In other words, it's reverse biased. We've got a depletion region surrounding the P material. The negative terminal here wants to repel the electrons of the N material, and the positive terminal wants to attract them. We have electrons moving in this direction. That means that our definition of current is actually flowing the other direction. This piece of silicon that's doped N-type really looks like a resistor. That's exactly what we're seeing over here, is that there's a linear variation of current with voltage. What would happen if we changed the gate source voltage and made it, say, minus 1 volt? In other words, this is minus 1 volt here. I'm going to show it this way as a plus 1 volt. And now we can calculate the voltage across the gate to drain. It would be this node voltage minus this node voltage. This node voltage is minus a plus 1, and then minus a plus 0.1. This would be a minus 1.1. Think of the transistor as an upper half and a lower half. This upper half has a voltage between the P and N. That's a minus 1.1, in other words, reverse biased. And between the bottom here, it's equal to a minus 1 volt. That's going to cause the depletion region to get a little bit larger. And that's going to cause the current to be more restricted. In other words, it's harder for an electron to flow back through this now because this difference, which we call a channel, is a little bit smaller. The resistance goes up, and that would cause the curve like this to go down because the slope here is conductance. This is a lower resistance than this one is. If we make this voltage more negative, or say let's make it equal to minus 2 volts, which would be 2 volts over here, this would now be a minus 2 minus 0.1. That would be minus 2.1. And so this upper half has a negative voltage across it of minus 2.1 in the bottom, minus 2. That's going to make that depletion region grow and even make the channel more narrow and make the resistance go up. That would be a curve like this one over here. We're in the ohmic region. The gate to source and the gate to drain are actually greater than the pinch-off voltage. Pinch-off voltage in our example on the previous page was minus 3 volts. What would happen if we were to make this voltage minus 3 volts? Make this a plus 3 volts here. This would now become a minus 3 minus a plus 0.1, so minus 3.1. And when you do that, the two depletion regions touch each other. And they now pinch off the channel. Like you're grabbing a garden hose and squeezing it, and basically nothing can flow. Under those conditions, the gate to source and the gate to drain are less than or equal to pinch off. All of what I just said is in words below and on the beginning of the next page. Let's next take a look at saturation. Again, let me apply a gate source voltage of minus 1 volt, which will make this a plus 1 volt. And now let's get out into this current saturation region by picking a large value of VDS. I don't know, say 5 volts. The gate to drain voltage is going to be minus 1 minus a plus 5 or minus 6. And likewise on this side we have a minus 6. The gate to drain is less than pinch off, and that means that these depletion regions are going to touch each other, pinching off the top of the channel. The gate source here, and also that same voltage over here, is greater than pinch off, and so these two depletion regions don't touch each other. Trapped in here are a lot of electrons, and this minus terminal wants to give them a shove. But there's a region here with no free charge. It's like the BJT. If we can give these charge a shove, like a bowling ball, get them rolling, and then this plus terminal of a very large magnet pulls them across. We get electrons flowing in this direction. We have a current, of course, flowing in the opposite direction. There's only so many electrons here. If we collect all of those, have them come out and come back in again, we get a constant current. That's what's going on over here. To be in the saturation region, the gate to source is greater than or equal to pinch off, and the gate to drain is less than or equal to pinch off. What I just described is also here in words below. These are the characteristics of a junction field effect transistor.